Hi, and welcome to Chapter 2. This chapter is all about polynomial and rational functions, and before we begin talking about them, we need to just do a quick trip down memory lane. We're going to talk a little bit today about complex numbers. You'll remember from your Algebra 2 class that the imaginary unit I is defined to be the square root of -1. That whole business about being able to have the square root of a negative number, that leads to a whole new set of numbers called the complex numbers, folks. Complex. Those are numbers that follow the form a plus bi, where a and b are real numbers. That is, they can be integers, fractions, irrational numbers like the square root of 2, real numbers. A is the real portion of the number, the real part. B is the imaginary part. So if you wanted to see how things fit in the complex number system, you have real numbers. That happens when b is equal to 0. That means there would be no imaginary part. You also have imaginary numbers. And again, that would be where b is not equal to 0. Okay? So the whole real number system is all part of this greater thing, the complex numbers. We're used to operating with real numbers. We're going to get more proficient at operating with imaginary numbers this year. We want to talk a little bit about how to do math with complex numbers. We will be adding, subtracting, multiplying, dividing, etc. We're going to begin with adding and subtracting, and to do those operations, really what you do is combine like terms. That is, you add real parts to real parts, I parts to I parts. So if I were going to add here, no number out in front, so there's no distribution, the parentheses don't have to be there. I'm going to add the real number part to each other. I'm going to add the imaginary parts to each other. So I'm going to end up with 8, -2 plus 3. 8 plus I is my answer for this one. And I would like you to pause the video and do this subtraction. Here's my work for that problem. Since this is a subtraction, we have to remember that you subtract everything inside the parenthesis. That is, 12 gets subtracted, but -I also gets subtracted. So a negative becomes a positive. Final answer there is -10 plus 7i. When you are multiplying complex numbers, the same things that work with real numbers extend to complex numbers. So you distribute things exactly the same way. One thing to remember though, I squared would be the square root of -1 squared, and when you square a square root, that gets rid of the square root sign. So I squared has a value of -1. That's going to make a difference for us. We're going to multiply these complex numbers, 7 minus 3i quantity times -2 minus 5i quantity. Quantity times quantity, I hope you're going to remember that's either the box method or FOIL, whichever one you use. Why don't you pause the video and let's use the box method to multiply these. Here's my work for this one. I set up the box with my two complex numbers, one on the top, one on the side. I did the box method, which is multiply row heading times column heading to fill in an entry in the table. When I got down here, I have to remember that I squared is the same thing as -1, so this is really saying 15 times -1 or -15. Then it's combine your like terms, and I have -29 minus 29i. So we've multiplied those complex numbers. Dividing complex numbers is a little bit different. You do that by multiplying by the conjugate of the divisor. And I hope that you'll remember the conjugate of a plus bi would be the same two numeral parts, a and b, but this time with a different sign in the middle. So these two are conjugates. When you multiply conjugates, I'm going to write them in here, a plus bi, a minus bi, you'll see that something cool happens. I'm going to use the FOIL method to multiply these. The initials FOIL stand for first, outer, inner, and last. This is only good if you're doing two-term parentheses with each other. This doesn't work if you have a minus bi plus c. You have to have two terms in each parenthesis. The F stands for first, so a times a is a squared. The O stands for outer or outside. And when you multiply there, you get negative ABI. The I stands for inside terms or inner terms. That's a positive ABI. You can see that those are going to knock each other out. And finally, L stands for last terms. So BI times negative BI, that's minus B squared I squared. Well, we know that I squared is negative 1, so that's going to affect that. These things knock each other out, and the end result when you multiply conjugates is a squared plus b squared. See, if this becomes negative 1 here, negative 1 times negative b squared is positive b squared. So when you multiply by the conjugate, what happens is you get rid of the imaginary number I from there. And that's what allows you to do the division. So we're going to multiply here. 3 minus 2i times 3 plus I, or you're going to multiply here, because I'm going to ask you to follow either the box method, which is fine, or follow the FOIL here, and let's multiply that out. Here's my work. I again use FOIL because that's what I grew up with. 3 times 3, 9. Outsides, 6i. Insides, minus 6i. Last, negative 4i squared. The I squared there acts as negative 1, so that becomes plus 4, and it washes out to be 13. So that leads us, see, that whole business of multiplying by the conjugate allows us to divide. If this is our division, 5 minus 3i divided by 1 minus I. The rule says you accomplish the division by multiplying by the conjugate of the divisor, and that's the one on the bottom. So we're going to multiply top and bottom by the conjugate of the bottom, 1 plus I. If we do it there, we have to do it here, 1 plus I. And we just have to do the multiplications. So we could box method on top and on bottom if we want. I'm going to ask you to pause the video and let's do this arithmetic. Here's my work for that. I multiplied 5 minus 3i times 1 plus I using the box method here. Remembering that I squared down here is like multiplying by negative 1. So that makes that positive 3. I did the box method for the denominators here. Again, that negative I squared acts like positive 1. Negative I squared, positive 1. So the denominator of 1 plus 1 is 2. 2 cancels into both 8 and 2, so we can reduce here, and the net result is 4 plus I. Okay, our goal, or part of our goal, is to be able to use those complex imaginary numbers to help us solve polynomial equations. Today we're going to talk specifically about quadratic equations, but you can also use them with any polynomial equation. A quadratic in general form, you will remember, has an equation like this: ax squared plus bx plus c equals 0. The quadratic formula many of you will remember by song, and I don't get the song, but you guys can. I just know the formula says you take the opposite of b over 2a plus or minus, and then it's the square root of b squared minus 4ac, and all of that is over 2a. Folks, I always write mine in two parts like this. Many people don't, so if you write yours this way, negative b plus or minus the square root of b squared minus 4ac all over 2a, that's just perfect as well. So the quadratic formula is used to find the roots in quadratic equations that are written in general form. We want you to use that here. We want our answers, it says, in simplest radical form. And right now I see the initial step here is going to have to be to get this equation to look like that. We want everything on one side equaling 0 on the other. So we're 3x squared minus 8x plus 7 equals 0. That means for the quadratic formula, a is 3, b is negative 8, and c is 7. Please pause that video and let's solve this quadratic equation. Here's my work for this quadratic equation. B is negative 8, so the opposite of b is positive 8. Twice a is 6. I just want you to be really careful right here. You're squaring the b term, and negative 8 times negative 8 is positive 64. Okay? And then minus, and I filled in the rest. Did the arithmetic. Out front we could cancel by a factor of 2, and here we have negative 20 under the radical over 6. Negative 20 is the same thing as negative 1 times 4 times 5. You take the square root of the things that you can. The square root of negative 1 is I, the square root of 4 is 2, and you have 5 left under the radical. That's all over denominator 6. However, this is all hooked with multiply, so that's when you can cancel, and you can cancel that 2 into the 6. So the final answer in its simplest radical form should be 4 over 3 plus or minus I times the square root of 5 over 3. Of course, you may have written it like this: 4 plus I root 5 all over 3 means the same thing, okay, both the same. All right, that's going to give us something to think about, and we'll talk about it in school tomorrow.